Welcome back, everyone. Techie here, and today we are doing a super focused, absolute zero fluff dive right into the mechanics of Redis. Now, if you recall our previous explainer on database indexes, you know exactly how critical fast data lookups are for a smooth application, especially when we were getting into the weeds of navigating B trees. Well, today we're taking that obsession with speed to the next level by looking at caching. We're going to skip all the unnecessary jargon and get straight to how you can make your data retrieval practically instantaneous. So in this explainer, we're unpacking in-memory storage, fundamental data structures, time-to-live memory management, and we'll break down the essential syntax like set, get, expire, and even atomic operations like INCR. All right, let's get right to it.
Section 1. How it actually works.
Okay, let's dive into this core physical analogy because it perfectly captures the underlying architecture here. I want you to picture a scenario. Imagine that every single time your app needs a specific piece of data, it has to physically get up, walk all the way across the room, and pull open this massive heavy metal filing cabinet just to find it. That filing cabinet, that's your traditional database. It is incredibly reliable, it's ACID compliant, it's persistent. Everything you could ever possibly need is stored in there safely. But the reality of checking it every single time you need a piece of info, it's just terribly slow. The bottleneck really comes down to disk I/O latency and query parsing overhead. Even with modern SSDs, fetching from disk is computationally expensive. Now contrast that with your desk. This represents Redis. Instead of walking across the room, Redis keeps the high-demand stuff constantly right there in front of you. It lives entirely in your system's RAM, completely bypassing the disk, which means your app's data is instantly available without the heavy lifting of standard queries.
So the absolutely crucial point here is the underlying logic. Caching is quite literally just the act of keeping that high-demand data right on your desk. By storing this information directly in memory, you're completely bypassing the hard disk. And to understand why this is such a massive industry standard, you have to think about the difference between milliseconds and microseconds. Traditional disk seeks take milliseconds, whereas accessing RAM takes microseconds. We're talking about performance that is orders of magnitude faster. Plus, Redis isn't just some simple key-value store where you dump plain text. It supports incredibly robust data structures. We're talking strings, lists, sets, sorted sets, and hashes. This means you can model complex objects directly in memory without having to serialize and deserialize JSON every single time you want to read or update a cache entry.
Section 2. Let's look at a real example.
And this brilliantly illustrates how we actually organize this digital desk. Working with Redis typically follows a very clean, three-step chronological lifecycle. Step 1, you have to intentionally store the data in memory. Step 2, you retrieve it when your app demands it. And step 3, which honestly is vital for keeping things running smoothly, you auto-clear it. This highlights a much broader architectural philosophy. Caching is inherently ephemeral. You're managing state in a highly constrained environment because, well, RAM is expensive. Auto-clearing isn't just about deleting old stuff. It's about proactive memory management and establishing strict eviction policies so your application never crashes from running out of memory. Let's look at how this builds using the actual commands.
To execute step 1, you just use the set command. By using the syntax set user-1042 techie, you are locking that string data directly into your in-memory storage, primed and ready for action. But, as we just discussed, strings are really just the beginning, and Redis provides tools to manipulate this data safely. Consider a scenario where you aren't just storing a static username, but instead you're tracking a highly active metric, maybe a page view counter or concurrent API requests. If you pulled the current number, added one in your application code, and then used the set command to put it back, you'd instantly run into race conditions where concurrent requests overwrite each other. Nobody wants that. So instead, Redis gives us specialized commands tailored to its data structures, like the INCR command. With INCR, you're telling Redis to perform an atomic increment directly in memory. It ticks the counter upward flawlessly, bypassing the need to fetch and rewrite, which keeps your data perfectly accurate at literal lightning speeds.
Now, what's really interesting here is just how frictionless the retrieval process becomes. When your app inevitably needs that user data again, it simply sends the get user 1042 command. Because we're using Redis and pulling straight from RAM, this retrieval happens with incredible efficiency. In computer science terms, fetching a simple key like this operates with an O of 1 time complexity. It takes a constant amount of time regardless of how much data is sitting in your cache. Just think about the massive contrast here. A traditional SQL database has to parse your query, traverse the B-tree index we explored on our previous explainer, physically locate the block on the disk, and then return the result. With Redis,
There's absolutely zero disk I/O involved. The system just hands the data right back to your application without even breaking a sweat.
But we do have to address step 3, managing the clutter. This is where TTL, or time to live, comes into play. By using the EXPIRE command with our key and a value of 3600, you're explicitly commanding Redis to automatically clear this specific piece of stored data in 3600 seconds, so exactly 1 hour. TTL is a critical safety net for 2 massive reasons: preventing stale data and protecting your memory limits. If you don't set an EXPIRE, that data just persists infinitely. Eventually, you will hit your maximum memory threshold. And when that happens, Redis is forced into reactive eviction policies, like purging your least recently used or least frequently used keys. Doing that consumes compute resources and can really degrade your application's performance. Setting a TTL basically functions like having an automated assistant who cleanly shreds old sticky notes the very second they are no longer relevant, keeping your memory completely optimized.
And honestly, that is caching live in action. You've seen how to transition your architecture from that slow, highly reliable filing cabinet to the lightning-fast, instantly accessible digital desk using core in-memory data structures. There's actually a full, extensive breakdown of these exact concepts waiting for you in the source material if you want to push this even further. So my question to you is, what specific part of your application's database is creating the biggest bottleneck for your users right now? Drop down and comment Redis for round 2, and we will dive even deeper into applying these caching architectures to complex tech stacks. Keep learning, stay focused, and I will see you in the next explainer.